Okay. Trick with 12 is this. In the first situation, they actually tell me what the gravitational attractive force between these two unknown masses is. Okay? They also don't tell me how far apart they are. Like, there's virtually nothing in this question that's useful, except what they tell me in the second part. So what I'm going to do is say, all right, that FG, whatever it was, okay, was calculated by going G times the two masses, and I'm just going to say that they were 1 and 1. Okay? And I'm also going to say that they were 1 meter apart. And I got that number. Now it wants to know what's the gravitational attractive force if you double the two masses and triple how far apart they are. So this is force of gravity in situation 1. In situation 2, this number is the same. Now that number is a 2, that number is a 2, and this number is 3 squared. So in the second situation, I have 4 times more mass, but I have 9 times on the bottom because it's 3 squared. So if I take this number here and I say the new number will be 4 over 9 times bigger or smaller than that number, okay, then I'll have it. So 3.24 e negative 7, okay, times 4 over 9. All that question is asking is, do you understand the relationship between mass and gravitational attractive force, and separation distance and gravitational attractive force? If you do, then you understand that by doubling the masses, both of them, you would have 4 times more gravitational attraction. But by tripling the distance they're apart, you would decrease the gravitational attractive force by a factor of 9. So you just go 4 times more mass divided by 9 times more distance, and boom, you've got the new factor. Okay? You don't actually need to know the real numbers. You just need to know what the effect of changing them would be. Okay? It's a bit of a math trick, okay, when it comes right down to it. But okay, it shows, if you understand those relationships, how you can get to it without actually knowing the real numbers. Okay? Everybody with me there? It's a bit of a tricky one for sure. All right. Well, let's go back to satellites here from yesterday. So we got to the point where we had done these 2 questions, and then I told you some useless trivia about how we name the moons in the solar system. Okay, so quick review from yesterday. Okay, all satellite motion is governed by this relationship. Newton's universal law of gravitation provides the gravitational attractive force that keeps a satellite in orbit. Okay, so anytime you see the word satellite, you know this will be true. FC will equal FG, okay, and you'll have that whole mv squared over r equals big G times mass 1 times mass 2, okay, over r squared. And that sometimes you'll have to do that substitution thing using this formula. You'd have to square it and plug it in for V sometimes. That will happen. And what will always happen to the mass of the satellite? It'll cancel. Okay? The mass of the satellite has no effect on the orbital speed or orbital period, okay, of the satellite. Okay, let's see if you can do this one. All right, we are looking for the period, okay, so how long it takes for Landsat, okay, to orbit the Earth 1 time. Okay, they give you some information there, okay, it says it orbits the Earth at a height of 912 kilometers. We want to find the orbital period. Okay, sorry, the thing I got this out of has this number wrong. Okay? The Earth's radius is 6.37 times 10 to the 6, not 0.60, or 6.38. Okay? Give you a few minutes on that one. Not mathematically terribly difficult, okay? But there is one little understanding trick in there. That was good. That's okay. Once you see if you can figure it out before I give it away.
Okay, anybody want more time on that one? Oh, electric recording the whole time. Okay, so we've got this this satellite's in a polar orbit. Doesn't matter if it's polar or equatorial; it's a circle. Okay, so we know right away that FC is going to equal FG. But we got to write down our givens. Obviously, it's orbiting the Earth. So mass of the Earth is a given. 5.98 times 10 to the 24 kilograms. Okay? The other thing they tell me is how far above the surface this thing orbits. Is that part of this formula? If I'm plugging this in where I've got mv squared over r, and I've got big G times m1 times m2 over r squared, what does r mean? It's the distance from where to where?
The center of the Earth to the satellite.
Right, the center of the Earth to the center of the satellite, which is not a huge deal because it's a small satellite. But if it was the moon, it would also include the radius of the moon. Okay, that r is always center to center. The most common trick that gets played in a satellite motion question is giving you orbital height, okay, altitude, or above the surface. Okay, those are keywords to look for. If they use those three keywords, it's a trick. Okay, and you need to remember that you're adding on the radius of the Earth. Or, if they ask you how far above the surface is it, you'll solve for r, which is center to center, and then have to subtract the radius of the Earth. Okay, but if you see those words, altitude, height, or above the surface, okay, you know that it's playing a trick with you about the Earth's radius being there or not. Okay, so they gave me the orbital height, but I actually need the orbital radius, which will be 912,000 meters, okay, plus 6.37 times 10 to the 6th. That will give me the center to center distance that I need for this calculation. Okay, so 6.37 E6, okay, plus 912,000. All right, so I've got 7.282, okay, times 10 to the 7, I think, right? No, 10 to the 6. 10 to the 6 meters. All right, so that's the center to center orbital radius now. Okay, now the question wants the period, not the speed. Two ways to do this. I could solve for the speed and then do a second step where I plug into v equals 2 pi r over t to get t. Or I could just substitute in 2 pi r over t right now for v. Okay? That's the way I would do it. Either way will arrive at the right answer. Okay? So I'm going to substitute in for v this formula, but obviously I'm going to square it. So that's going to mean m for pi squared r squared over t squared, and then that r is still there. Okay, and then on this side, this doesn't change. Big G times the mass of the Earth times the mass of the satellite over r squared. Okay, so now I've got t in there. I've got to do a little cleanup because I've got an r squared on the top and an r on the bottom. So I'm going to get rid of any unnecessary r's. Okay, so that r will go away. That squared will go away. Now I'm good to start manipulating. Right? I want to solve for t. Right now t is on the bottom, so I want to move it over here. Okay, so I got t squared there. Then I'm going to move everything else over to the other side. Okay, so I'm going to move the r squared first. What's r squared times r? R cubed, right. Okay, so now that's gone. And then I'm just going to divide all of this stuff over here. Mass of the satellite's going to cancel when I do that, so I'm going to get rid of it now. And then I'll just have big G times the mass of the Earth. So now those are gone. Okay, and then square root, and I've got t squared. Or sorry, just t, because I'm square root. That's the whole point. Okay, now that I've got that, now I can plug in my numbers. So 4 pi squared times 7.282 times 10 to the 6 cubed divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Okay, so a little bit of an adventure here with our math.
Okay, so 4 pi squared, okay, times 7.282 E6 cubed, okay, divided by 6.67 E negative 11, 5.98 E24, bracket, bracket, bracket. That should close it all up. Okay, so the orbital period of Landsat is going to be 6,182. Actually, we only have 3 significant digits there. So 6.18 times 10 to the 3. What are my units? I just put forces equal to each other to start. I had newtons equals newtons. Okay? What's my units for time when I do this? A newton is a kilogram meter per second squared. So what are my units for time? Seconds. This is in seconds. Okay? 6.18 times 10 to the 3 seconds. Okay, so that would mean 1.7 hours. Okay, rough. All right. Everybody okay with that? All satellite motion comes down to that. FC equals FG. Sometimes you have to do that substitution, yes. Okay, but there's no other tricks here other than that whole height, altitude thing. Okay, there isn't any other way to make you do any more complex math than what we just did. Okay. All right. I want you to try those two. Very similar to what we just did. All right, so the International Space Station orbits the Earth at a height of 359.2 kilometers. What do I need to do with that number? Add it to the radius of the Earth. That is not the center-to-center distance. That's from the surface to the International Space Station. So the true radius will be 6.37 times 10 to the 6 plus 359,200 meters. Okay, so that's the first thing we have to do is get the proper orbital radius. So 6.37 E6, okay, plus 359,200 meters. All right, so 6.7292 times 10 to the 6 meters. Now I've got R. Okay, I also know that it's orbiting the Earth, so the mass of the Earth is a given. Okay, and I know it's a satellite, so right away I know this is true. Right? I'm only looking for its orbital speed, so I don't have to do any substitutions. mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Okay, so mass of the satellite's going to cancel. I'm going to move r over here. When I do that, it's going to cancel the square on the r down there, and then I'm going to square root to get v. Right, so our calculation will be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, and then divide that by 6.7292 times 10 to the 6. And we'll have our answer. Now sometimes the answer here is off just a bit because this book uses 6.38 for the radius of the Earth and 5.97 for the mass of the Earth. So their numbers are slightly different than ours. Okay, so we'll punch in what we have. Okay, so that'll be 6.67 E negative 11, 5.98 E 24 divided by 6.7292 6. All right, so the orbital speed of the International Space Station, okay, should be, yes, so it came out to this two slightly different for us. For us, it should be 7.70 times 10 to the 3 meters per second. Okay, everybody all right with that?
That's nearly 8 kilometers per second, which is how fast we said you'd have to go if you were near the Earth's surface in Newton's thought experiment the other day. Okay, so the International Space Station is trucking along there in outer space. All right, how many people have done number 2? All right, I'm going to give you a few more minutes on number 2. Okay, it's very similar to the one we did on the last screen. Okay, so you can kind of refer back to your method there if you're a little lost. One here. Okay, so as I said, the second one works just like the example we did previously, but they did, of course, give us altitude again. Okay, altitude is, of course, measured from the Earth's surface, not the Earth's center. Okay, so we do have to do that radius calculation again, 6.37 times 10 to the 6, plus now 114,593,000 meters. Okay, the Chandra X-ray satellite has to be high enough that it's above our Van Allen belts, okay, above kind of the magnetic field of the Earth. Otherwise, incoming X-rays from the sun, they get slowed down. That's why we get auroras that can interfere with its operation. So it has to be much, much higher up. Okay, so we have FC equals FG. Okay, that's going to be mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. But I'm looking for orbital period, so I'm going to do that whole substitution thing. Okay, in doing that substitution thing, I'm going to take the mass of the satellite out right away. Then I'm going to take v squared out as well, and I'm going to put in this for v, okay, and obviously I'm going to square it. So 4 pi squared times r squared, and then t squared is on the bottom. Okay, then I'm going to start manipulating. So I'm going to bring t squared over to this side. Okay, I'm going to cancel this r completely and get rid of that square. Then I'm going to bring r squared over here. So r squared, okay, times r is going to be r cubed. Okay, so now that's going to be gone, and then I will bring the big G times the mass of the Earth over to this side as well, and then square root everything. Okay, so yeah, it's a bit of a manipulation challenge. Okay, so 4 pi squared times our 114. Oh, sorry, we actually didn't calculate what that was, so we should probably do that next. Okay, so 6.37 E6, okay, plus 114,593,000 meters. Okay, so there's our overall radius. So we'll plug that number in. It's going to be 10 to the 8, so 1.20963 times 10 to the 8 meters. Okay, and that has to be cubed. Right, over 6.67 times 10 to the minus 11 times the mass of the Earth, because that's what it orbits, and times 10 to the 24. Right, so 4 pi squared, okay, close the brackets, 1.20963 E8 cubed, those, okay, divided by 6.67 E negative 11, 5.98 E24. Okay, so we're looking at 4.19 times 10 to the 5 seconds, okay, which is exactly what they got. So. Okay, everybody with me there? All right, there's only a few ways that those kind of questions can be asked. Okay, we've done now one that asks for orbital period, one that asks for orbital speed. The other thing could be, you could get what's the orbital height, or orbital altitude, or orbital radius. Okay, you could also be asked, it's pretty odd, but it could happen, what's the mass of the planet the satellite is orbiting? I can't remember ever asking that, but it is one thing you could get if you had the right combination of givens. Okay. All right, questions on how that one worked?
Okay, I would like you guys right now, okay, I'll put it up here on the board, but there's some satellite motion questions in your workbook, okay, only 6. There they are. I'd like you working on that. Okay, when we get done that, we'll probably talk about gravitational field strength a little bit today. Okay, tomorrow we'll kind of finish that stuff all up. And then Friday obviously is your quiz. Okay, this quiz will be on vertical circular motion only. So, since your unit exam is next week, you're not going to have any quizzes on satellite motion or gravitation. But, okay, we will do an assignment on that Monday or Tuesday, whichever day I don't do the unit review. Okay, so you'll have some practice there. Okay, so if we want to calculate the time of 1 year on Mars, that's the orbital period of Mars, right? So we're looking for big T. Okay, that's our question mark. We do know that Mars is a satellite of the sun. So we can set it up like this. Okay, mv squared over r, this will be the mass of Mars, okay, equals big G times the mass of the sun times the mass of Mars over the radius of Mars's orbit squared. Okay, so this is the same r on both sides. Since I'm looking for orbital period, I don't want v in here, I've got to do that substitution, and mass of Mars is on both sides, so I'm going to quickly get rid of the mass of Mars and v squared. And I'm just going to plug in 2 pi r over t. Okay, so there's 2 squared, pi squared, r squared, t squared. Okay, so I've done that substitution, and then I'll get rid of the things that are doubled up. So this r is going to go away, and that squared is going to go away. So I want to manipulate for t. I'm going to bring t over here. Okay. Going to divide both sides by big G times the mass of the sun, so that's gone from this side. And then I'm going to multiply both sides by r squared, which is going to give me r cubed, and then I'm going to take the square root of that to get rid of the square here. When I plug in my numbers, okay, 4 pi squared times the radius of Mars's orbit, which was... Oh, there it is. Okay, 2.3 times 10 to the 11 cubed, okay, divided by 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, the mass of the sun. Okay, so we will have, and this one I'll do piecemeal. Okay, so I'm going to go 4 pi squared and just it equals. Okay, and then I'm going to multiply that by 2.3 E11, and I'm going to cube that, so math 3. Okay, now I've got the top done. Okay, now I'll divide that by what's on the bottom, which will be 6.67 E negative 11 and 1.99 E30. Right, whoops, not 10. Close that up. All right, so I get 3.62 times 10 to the 15 seconds, okay, which if I divide that by 3,600, it's that many hours. Divide that by 24, it's that many days. Oh, sorry, I forgot to square root that number. Hang on. I got to square root that number. Okay, so there it is in seconds. 6.0 times 10 to the, 7? Yeah, okay, which is the same as 1.9 years. So you can totally do it piecemeal, and it probably is easier. You don't have to keep track of brackets. Okay, any other questions? All right. What I want to quickly talk about here, we won't kind of go into the full lesson because we won't have time. Okay, but tomorrow we are going to cover gravitational field strength, and that is this formula on your formula sheet. Okay, big G times M over R squared. Okay, so that formula will calculate, what does little g usually stand for? Acceleration due to gravity, right? Okay, well, acceleration due to gravity is also called gravitational field strength. It is what you would feel as an acceleration
between the two objects that are attracted to each other. All right? Now, this formula is not a new and separate formula. This formula is simply this. Force of gravity equals, oddly enough, the force of gravity. I mean, they better be equal, right? But what we're saying here is there's two ways to do this. There's this way, and there's this way. Those two numbers should be equal, no matter where I am, right? But we don't always know what little g is. This relationship allows us to calculate it because all things fall at the same rate regardless of their mass. Okay? So if I have something caught in Earth's gravitational field, okay, it doesn't matter whether that something is 10 grams or 4 million kilograms, it is going to have the same gravitational acceleration at the same point. Okay? That is why the smaller mass will cancel. The acceleration is generally due to the larger mass. The smaller mass is, generally going to accelerate towards the larger one. Okay, so that smaller mass is what's on both sides. Its acceleration is the same regardless of its mass, so it cancels, and we're left with that formula we started with. So it's really Newton's universal law of gravitation, but we simplify it down to, instead of calculating the force pulling the two together, the rate at which they move together. Right? Now here's the weird thing about this. When you do this calculation, you can get different units. What are the units usually for g? Meters per second squared. Okay. If you do this, okay, you're going to get newtons per kilogram. Is that okay? It absolutely is. What are the units for a newton? Oh, here we got to think back. Okay, we calculate a newton. That's mass times acceleration. Okay, so a newton is a kilogram meter per second squared. Well, if I divide that by kilograms, what do I get? Meters per second squared. Okay, so you could get a gravitational field strength with the units of newtons per kilogram. I would totally do that to throw you off. Okay, but those units are exactly the same. Okay, but suddenly seeing it not meters per second squared really messes with people's minds, and I like that. So yeah, I would totally do something like that. All right, we will leave it there for today. Tomorrow we're going to go into that in more detail, go over some stuff to do with that, and depending on how much time we have, we might do our unit exam review tomorrow. Okay, we'll see kind of how it goes.